Hi everybody, Knowledge Academy welcomes you. In our previous video, we discussed about the classification of digital logic circuits. In this video, we will be discussing about the basic fundamental unit of combinational circuit. Okay, so logic gates are the basic fundamental unit of combinational circuits. We are going to discuss about that. Before entering into the video, kindly subscribe my channel Knowledge Academy. All right, now let us enter into the video. Okay, so this slide shows NOT gate. For a NOT gate, when an input A is given, the output will be receiving is as A bar. And this is the symbol of NOT gate. Just look at the truth table. When the input is 0, the output is 1. When the input is 1, the output is 0. Which means the inputs can be considered as switch and the output can be considered as a load. For example, a light, a bulb. When the switch is in off position, the light glows. When the switch is in on position, the light does not glow. So this is NOT gate. So very simple. This slide clearly shows the information about AND gate and NAND gate. First we shall discuss about NAND gate. Right? This is the symbol of AND gate. These are the inputs A, B, and the output we are getting as A dot B. So we should not say it as A dot B. It is better to say it as A and B. Because when we say dot, we can consider it to be multiplication. Right? But it is somewhat related to multiplication. A and B. So A and B means when both the switch, A switch and B switch are in on position, only then the bulb will glow. So that is the meaning. That is why we call it as AND gate. When the switches A and B is in on position, the output will be received. Right? So let us check it in the truth table. Right? So here this is A switch and this is B switch, position of B switches, and this is the this indicates the status of bulb, the load. Right? So here both the switches are in off position, the bulb is not glowing. Here in these two conditions, here B is in on position, whereas here A is on position, whereas only one switch is in on position in these two cases, so the bulb is not glowing. Whereas in the last condition, both the switches are in on position and the bulb is glowing. We are getting the output. So A and B are in on position, we are getting the output. So that is AND gate. Right? Now let us come to NAND gate. NAND gate is the reverse operation of AND gate. Right? So this is the symbol of NAND gate and the expression is A dot B the whole bar. For AND gate it is A dot B, whereas for NAND gate it is A dot B the whole bar. That is, it is performing the opposite operation of AND gate. For AND gate, when the switch A and B both are in on position, we will be getting the output. Whereas here we do not get the output when the switch A and B are in on position. So that is NAND gate. When the switch, let us look at the truth table. When the switch A and B both are in on position, we are not getting the output, whereas for all the other cases we are getting the output. An opposite of AND. Right? So this slide shows the information about OR gate and NOR gate. Let us discuss about OR gate first. This is the symbol of OR gate, and we are giving two inputs A, B, and the expression is A plus B, and it is good to pronounce it as A or B. Okay, so here it obeys like this. When the switch A or B is in on position, we will be getting the output. The bulb will glow. Okay, so that is the condition, right? When the switch A or B, any one switch, when the switch A or B is in on position, so it is not necessary that both the switches should be in on position. When the switch, any one of the switches, okay, here B is in on whereas A is off, but we are getting the output. Here in this condition, A is on, B is off, but we are getting the output, right? Here both the switches are on, again we are getting the output. So it is the thing is, among these two switches, if any one of the switch is in on position, the output will be received. And here we have to be very careful with the last row of the truth table, 1 1. So sometimes students may mistake it as 1 plus 1, they may write here as 0. So it is not adder. If it is adder, 1 plus 1 is 0 and 1 can be a carry, but it is not an adder, it is an OR operation. So it is more wise to consider these two things, these inputs as switches and this one as a load, a bulb. So when the switch is on, when both the switches are on, the bulb is glowing. So we can consider it like that. Okay, so if we do not have this kind of consideration, we may consider there is a chance of writing 1 plus 1 as 0, because the symbol of the mathematical, the expression, logical expression of OR gate is A plus B. We write the plus symbol. So that is why. In order to avoid these confusions, we can consider consider it like this. Right. Now let us discuss NOR gate. NOR gate is opposite of OR gate, and this is the symbol of NOR gate, OR gate with the bubble at the end. So that indicates NOR gate, right? And the logical expression is A plus B, the whole bar. When A and B are given as input, the output is A plus B, the whole bar. That is, when the switches A or B is in on position, the bulb does not glow. Okay, whereas in OR, we had when the switches any one of the switch A or B is in on position, the bulb glows. Here, when the switch A or B is in on position, the bulb does not glow. We will not be receiving the output. So that is shown here. When the switches A or B is in on position, there is no output. The bulb is not glowing. Right? When both the switches are in off position, the bulb glows. Okay. So this is NOR operation. Right? Now, this slide shows the information about XOR gate and XNOR gate. Let us discuss XOR gate first. This is the symbol of XOR gate, right? AB is the input and the output is A bar B plus AB bar, which can be written as A XOR B, and the symbol of XOR is plus surrounded by a circle. A XOR B, right? So here XOR gate, it gives the output when the inputs are different. That means both the inputs, both A and B cannot be same. Both A and B cannot be 0, both A and B cannot be 1. If both A and B are 0, or if both A and B are 1, there is no output, right? If they are different, there will be output. Okay. Just look at the truth table. In this case and in this case, the inputs are same. Both are 0, both are 1, and there is no output. Right? Whereas in these two cases the inputs are different. A is 0 here, B is 1 here, and we are having the output. A is 1 here, B is 0 here, again we are having the output. Okay, so this kind of operation is performed by XOR gate, right? Now let us discuss about XNOR gate. This is the symbol of XNOR gate with a bubble at the end, and this is the mathematical expression for XNOR gate: A bar B bar plus AB, right? And here the symbol A XNOR B can be written as A dot surrounded by a circle B, so we call it as A XNOR B, and it is performing the opposite operation of XOR gate. Okay, so when both the inputs are same, we will be having the output, and if the inputs are different, we will not be having any output. Just look at here, the inputs are same, both the inputs are same, both the inputs are 0 here, both the inputs are 1, and in both the cases we are having the output, right? Whereas for the other two cases the inputs are different. In this case A is 0 and B is 1, whereas in this case A is 1 and B is 0, and we do not have any output here. The bulb which is connected at the output is not glowing, right? So this kind of operation is performed by XNOR gate, right? So out of all these gates, we call NAND gate and NOR gate as universal gates. The reason is we can design all the other gates using NAND gate. Similarly, we can design all the other gates using NOR gate. So in a circuit, we can design entire combinational circuit only by using NAND gate and only by using NOR gate also. So that is why we call NAND gate and NOR gate as universal gates. So with this, I am concluding this video. Thank you for watching this video, and if you like, kindly comment and share, and don't forget to subscribe my channel. Thank you for watching this video. Again, meet you again in the next video. Until then,